And I'll begin just at the very beginning. So this is a fourth year of our seminar series. The seminar series evolves with time. It is based on our NASA Enigma program, which stands for the evolution of nanomachines in geosphere and microbes and microbial ancestors. And the idea is to understand, how did proteins evolve to become the predominant catalysts of life on Earth? Now, I know some of you, and with all due respect, I understand, some of you like the RNA world. Proteins have a lot more complexity than RNAs, and they obviously are the dominant catalysts of life on Earth. And so we focused on oxidoreductases, which I'll get to in a moment. And the reason for that is rather obvious. If we're interested in evolution of life, we need to understand how life got energy. And so the oxidoreductases are responsible for generating energy in all life forms on this planet. And the Enigma program contains about 45 researchers from across the world. And we're integrated in 3 themes, which are not with hard boundaries. So we have postdocs that work across the boundaries, graduate students that work across the boundaries, and obviously the leaders of the themes have to talk to each other. So we're not a micromanaged group. I don't micromanage. I'm trying to synthesize information, not to tell people what to do. And the theme 1 is synthesis of the nanomachines, we call them, in the origin of life. So what were the very earliest peptides or very small proteins? There's obviously a fuzzy definition of what a peptide is, that allowed electrons to move with or without protons. And that theme is led by Vic Nanda, who's in the Center for Advanced Biotechnology and Medicine and in the medical school in the Department of Biochemistry. And he and I have collaborated for many years. Long before we were funded by NASA, we were funded by the Gordon and Betty Moore Foundation for, I think, around 10 years. And Vic's specialty is really in designing peptides, designing proteins. So that's theme 1. Theme 2 is a bioinformatics theme writ rather loosely. So it's understanding how these nanomachines evolved over time in organisms. So what were the first protein folds? That's probably one of the most common things that connects theme 1 and theme 2. So Rossmann folds, ferredoxin folds, how these folds became evolved into developing the large, very complex proteins that we see today, which obviously didn't just come out of nowhere. So when we talk about large proteins, obviously one of the themes we're going to talk about in the talks today concerns nitrogenase, which is a Rube Goldberg apparatus, if I ever saw one, of nanomachines. And theme 3 is how did these nanomachines appropriate the transition metals and the mineral structures, in effect, in many cases, from the geosphere. And I should say theme 2 was led by Jana Bromberg. Theme 3 is co-led here at Rutgers by Nathan Yee and by Bob Hazen and Shauna Morrison, who are at the Carnegie Institute of Science in Washington. And so we have these three groups, if you will, loosely interacting. And the focus is on, as I said, the oxidoreductases, because the evolution of metabolism is key to understanding the origins of life. This is our hypothesis, or at least our assertion. Now, in the Dayhoff world, which many of you know better than I, Margaret Dayhoff was the mother of bioinformatics, if you will. Some of these enzymes are extremely ancient, and ironically, because they're ancient, they're highly conserved. So when you have a machine, even if it doesn't work as well as it could, such as Rubisco or photosystem 2 or even nitrogenase, it turns out in the Microsoft world of biology, you don't destroy the machine and invent a new one. You just fix the old ones. Or you make the old ones more and more and more complicated. And that's exactly what biology has done. So we can find many, many, many machines that are really responsible for life that are extraordinarily conserved. If we take, for example, the D1 protein, which is one of the core proteins in photosystem 2, which is responsible for water splitting, it is 86% conserved from a cyanobacteria to an oak tree. That's over at least 2.5 billion years of evolution, if not more. And in mitochondria, obviously, we can see huge amounts of conservation of the oxidoreductases. So one of our foci has been, if not a major foci, reverse engineering their evolution. How can we figure out how these proteins evolved? And understanding, if you will, boldly speaking, the origins of life through the evolution of the core metabolism that was responsible for obtaining energy in these organisms and moving them far away from non-equilibrium thermodynamics, from equilibrium thermodynamics. So if I can have the last slide, please, that'll be my final talk here, is the three themes are broadly shown here. We have the issue of going from prebiotic catalysis to biotic catalysis, the origins of peptides, and their ultimately their autocatalytic processes that allowed them to recreate themselves with or without an RNA world or a DNA world. And then we have the evolution of those machines. So we're talking about protein evolution writ broadly, but focusing to a large extent on the oxidoreductases and the folds that were responsible in the beginning for moving electrons. And then theme three puts this in the context of geologic time. Most protein biologists are not very well aware of evolution beyond, for example, the Phanerozoic, the last 600 million years or so of life's history. The first 3 billion years of life's history are obviously very poorly written in the geologic record. We don't have dinosaur teeth 3 billion years ago. It's very, very, very difficult to find actually microbes in the rocks, but we can find evidence of microbial evolution in many ways, including potentially their lipids, the isotopic composition of the elements that they transformed, such as sulfur, nitrogen, to some extent, carbon. So we have records of these molecules and atoms for a very long period of geologic time. And trying to connect the changes in the isotopic record or lipid composition to the evolution of metabolism has been one of the challenges that we have faced in over many, many years. So without further ado, I just want to put a few bookkeeping things in order here. The questions at the end will be moderated via chat by the moderator. And if there is a jargon in the talks, either the moderator or I or one of the other hosts will interject and say, what does that mean? Because we really want to make this as broadly accessible as possible. And it's very easy for structural biologists or molecular biologists to fall into jargon unintentionally. And so that's what we'll be doing. Each speaker will have approximately 45 minutes. They'll be followed with a Q&A, and then we will have a postdoc in each case that will give a talk that is related to what the speaker has talked about. And that gives the postdoc an opportunity to explain what they're doing and their interests in the Enigma program. And I just want to make sure that I thank all the speakers today and the speakers yesterday. And I also want to make sure that we all give a large shout out to Beatrice, who has organized this and has been a yeoman for many years working with me. But she makes these types of symposia possible, and it is without her, I don't know what I would be doing.